Hello everyone, welcome to this student's introduction to VLMs. So VLM stands for Vision Language Model. My name is Jeremy. I'm a computer science undergraduate student at NTU Singapore. So when we talk about VLMs, we are really thinking about this model that can process both text and visual inputs, maybe image or videos, and outputs some kind of response, maybe a description relating to that visual input, maybe follow some kind of instruction that derives from both the visual and the text inputs. And we can train those models on our specific use case. So this field is still relatively new. And the reason why I'm making this is really to motivate a new resource which we have called the nanoVLM. I will explain about this later. So since this is a student's introduction, so I would expect some kind of background in statistics and a bit of machine learning. But if you're still new and you're trying to get everything out of this video, just keep on until the end. And if you don't understand, you can look things up along the way. All right, maybe before we start, let's motivate ourselves about why we will study VLMs. My personal answer will be very interesting. It's kind of obvious, but how interesting? So, firstly, if we imagine what humans can do when we try to perceive information around us, we use sensors, we use our eye to see things, we use our tongue to taste things, we use our skin to touch and feel things. And then, of course, whenever there are images, we are going to see and we can read text as well. So if only we have this one model that can mimic what humans can do, well, that's multimodal models where we have different modalities or information types that we can sense using our sensors. And VLMs extend text traditional capability of natural language models to vision. So yeah, think about how we can use our eye and our brain to process both image and text. And this is where the two giants of two academic fields, NLP, natural language processing, and CV, computer vision, interacts. And as an academic myself, I'm actually really interested, and if only you can see the magic behind how we can instruct a model. We have an image, we have text, we have prompts, and then it's going to output exactly what we want them to be, not in a sense, but at the very least, we can see that the model kind of responds us like a human, right? And so this is, I think this is a controversial opinion, but multimodal models is one of the frontiers that leads to AGI, or artificial general intelligence. Basically, if we dig on this field long enough, eventually we'll get a model that can do everything that humans can do. It's still a long way, but I think I'm actually quite optimistic in this field. Okay, so this new resource that I'm going to explain is nanoVLM, which is the simplest repository to train your vision language model in the pure PyTorch. So in total, they amount to about 500 to 600 lines of code, where you combine your image processing capability, you combine your text processing capability, and combine them so that you can have a model that takes both image and text as inputs. That might not sound really interesting, but 600 lines of code is the least things you can hope for when you can try to model how we can see and we can read text. So it's really interesting. And if you're interested, I highly suggest you to go and check the GitHub repo as we go through this video and take a look at the modules that I'm going to explain in more detail. All right, now let's think about how we can design a system that can take image and text as inputs, and it's going to output a text response. So at this point in time, we already have the technology to process text inputs into text response. We can train them to respond in whatever way that we want to, maybe follow instructions and everything. We have a technology that we can compress image or visual informations into a representation that we can eventually train the model on, and it can process in a human-like way. But we don't know how to combine them, right? So just going to explain the components here. We have this vision encoder that can encode or basically turn this image information into numbers that we can train the model on. But we'll still need to translate the vision words or language into text language so that they belong in the same language or space or something like that. And this is done by using this modality projection. After that, we can think both vision and text are already aligned, and we're going to process them using the language decoder, and then we get the response that we want. Okay, so the first component is the language decoder. In this case is the LLaMA architecture. So essentially the motivation for this is to have the text input, and then you have a text output, but the objective that this model is originally trained on is to do the next token or next text prediction. So this is some kind of autocomplete where, for example, when we think about what we want to say next, the words that we are going to choose comes from the vocabulary, but we take context of what we have previously said to think about what is the next word that is appropriate for our next response. So in this model, I'm going to explain about the technicalities behind this. What are the operations? We have RMSNorm, we have the rotary positional encodings, we have the grouped multi-query attention here, and then we're going to discuss about the feedforward and sampling. So let's just get whatever details that we can get out of this LLaMA language model. Okay, so the first information is the RMSNorm. So this happens 3 times, here, here, and here. And the motivation of doing this operation is really when we have a tensor or a table of inputs, we are trying to normalize them so that they have kind of the same range of values. And the reason this is important is for calculation stability, which will relate to the training. So it's purely numerical stability that we are trying to achieve. And so this is the operation that we have. But to make it really simple, the input for the transformer architecture in general, of which LLaMA is one of them, is we have the batch dimension, we have the sequence length dimension. Like for example, we have the IM not here, which is a sequence. So each dimension here indicates a new word or a new token, and then we are going to have the hidden dimension. So each of the word, it has a numerical representation, usually a vector, and then this operation is applied so that first we try to find what is the mean of the square value. So firstly, we square all of the elements inside this table, and then we're going to find the mean or the average value of each of the elements. We are going to find it row by row. We're going to combine from this output, the mean, we're going to copy and paste column-wise so that it matches the original dimension, divide element-wise, and then you're going to multiply the output of that operation with this weight parameter gamma here. So the parameter gamma is actually a vector that is trainable, and it's a vector, so we're going to repeat that for every embedding dimension so that they have the same value of parameters. Okay, so the next piece in our architecture is the rotary positional encoding. So positional encoding is essentially how we can introduce positional dependency so that the model processes each words in the sentence in order that they appear, so the words are not shuffled around. Only this time you're going to include this relative position difference so that when we have 2 words in a sentence, the way that they are related in a positional way is through their relative difference in position in that sentence. Okay, so suppose that we have a sentence here like cats chase mice quickly. For each of the words, we are going to have a position ID. And then again, for each of the words, we are going to have the embeddings or the vector representation representing that word. Okay, so we're going to divide this embedding into dimension pairs. So for example, if we have the 4 dimensions vector for each of the words, we're going to divide them 2 by 2. Okay, and then we're going to compute this quantity based to the power of something. So the numerator is actually the pairs on whichever the vector is actually belonging from. Like, for example, we have this portion over here, which is the first pair. So that's why they have a numerator of 0, because that's actually the first position. So we process them in pairs, like 0, 0, 2, 2, corresponding to the pairs. Like, and then the denominator is actually the length of each token. Oh, sorry, the length of each embedding dimension. Like, for example, we have for each of the words, we have a 4-dimensional vector, and that 4-dimensional vector is going to be in the denominator. And then for each of the word, we are going to multiply that by the position. Like, for example, in the first row, it corresponds to the word cats, and then the second row is the word chase, and then so on. So 0, 1, 2, 3. So this essentially encodes the position of the ordering of each word, along with the pairs of the dimension of the hidden dimension or the embedding dimension. So we have a representation based on how the words appear, and then we have a representation based on how each words are represented into pairs. And we're going to compute the cosine and sine element-wise on this matrix, and then we are going to rotate, going back to this embedding vector. Suppose that in each pair we have x, y here. We are going to rotate 90 degrees so that it becomes negative y, x. We're going to do the same thing for each of the pairs. And then we're going to calculate this cosine plus the rotation of 90 degrees, which is actually just this output, multiplied by the sine element-wise of this. So if you have prior background in complex numbers, you're essentially rotating the matrix by m theta counterclockwise, or it's the same thing as multiplying them by a complex exponential e to the power of I m theta. And so now you can assume that each of the words that appear is already positionally encoded and they are not shuffled around. Alright, this is where things get interesting, because now we are trying to kind of customize the meaning of a word corresponding to the context or the sentence in which they appear. For example, suppose that we have the word bank. So that can mean bank as a financial institution, or it can be bank like river bank or something like that. So the meaning depends on the context that we in which the words appear, right? And so we are going to customize the generic representation of each word into a contextual one. Okay, so let's go back to our batch sequence length hidden dimension, which is the general input form for the transformers. We are going to multiply this matrix by WQ, WK, and WV so that we can get the key, query, and value. So these matrices are trainable parameters, and they are trained alongside the model. And then, let's ignore the notation for a while and think about the notations names, like keys, queries, and values. So let's think about query and keys first. So when I put the sequences side by side like this in a grid-like form, I want you to think about it like this. Suppose that my query is I, right? So now I'm going to ask a question. Which words in the same sentence that is actually most similar to I, or it has the most contribution in the meaning to the word I? And that's the key value that I'm going to choose. So the way that the values here are computed is by dot product of each of the words. So for example, when I get this QI, it's actually the embedding vector of the word I, that is the query. And then when we think about the KI, this is going to be another vector that's computed, but this one is depending on the I as a key, right? So we get this kind of similarity score that we are going to normalize by softmax so that they are positive and they sum to 1. So basically the dot product here, they can have negative values, and each of the rows, they do not sum to 1. So maybe you are confused, like, why do you want each of the rows to sum to 1? And think about it like this. So when I ask what is the most similar word to I, of course I'm going to look at the words in the sentence, and then each of them should have the sum to 1. So we get this kind of like scoring or weighting between 0 to 1. And I can see that, for example, here, not contributes the most in meaning to I, and I and M contributes 0.1 and 0.2, which is not as much influence as not, right? And this way we can kind of like weightage and change the meaning of the word I depending on the sentence that they appear. And then after that, we have computed the matrix multiplication. And yeah, don't forget that after computing the matrix multiplication, we're going to divide that by the square root of hidden dimension. And then yeah, we are going to multiply that by phi. So phi is actually another representation of the sequence. But now we are going to infuse that kind of contextual meaning so that finally we can get an output so that each word will have its customized meaning depending on the context or the sentence in which they appear. Alright, so the previous operation, which is the scaled dot product attention, is only a single head operation. So now we are going to discuss the multi-head operation of that. So what I mean by multi-head is that, firstly, remember that in the previous slide, we have the input of batch sequence length, hidden dimension. So we're going to divide the hidden dimension into smaller heads. So when we think about the embedding factor, we're going to split the embedding dimension into smaller parts, right? And they should sum to hidden dimension. And then for each of the hidden dimension, we will have its own query head. We have its own key head. We're going to do the operation, the attention as shown before, and then we are going to multiply the output or the similarity score with the value head. And we will get, for each of them, the attention value for that dimension split. And then we concatenate all of them, again, into the same dimension as the original Q, K, and V. And then we are going to multiply that by this WO, which is, again, another parameter, so that the output is still batch, sequence length, hidden dimension. So why would we do that? The first reason is for parallelism. Each of the dimensions heads, they can be processed independently. But more importantly is to capture various dependencies by multiple heads. Like, for example, suppose that this head over here will have each of the tokens corresponding to a different kind of similarity. And then the other head finds another different similarity score, so that each of the different heads, when we combine them together, we will have already different kind of scorings or different kind of perspectives that we get, compared to when we get only using a single head attention. Alright, now let's take a special kind of attention operation, which is the masked attention. So let's discuss first about the causal language modeling, which is used in decoder-only language models. For example, we have the attention score, as we have shown before. We have multiplied the Q and the K matrix, but now we are going to apply an upper triangular mask. So before we get into the deep detail, there is a motivation to do this. Basically, the model that we are trying to train is the model that does auto-completion, right? But if the model that we are going to train is going to do auto-completion correctly, for example, I have the first word I, and then the next word is going to be I am. The next sentence is going to be I am not. We are going to complete each of the words and add them sequentially. In the beginning, it must not have any knowledge about the final sentence, right? Since we are going to append words word by word, right? And so it will be some kind of data leakage or some kind of cheating the model if it already know the sequence that it's going to autocomplete. And so we are going to apply mask of negative infinity. And so the reason why this is upper triangular is that, for example, in the query I, you only have the access to the first token. In the second query M, you can have the context of I and M, which is itself. And in the third one, you can have the context of I, M, and not, which is the complete sentence. So in any of those words, I cannot access M in the first stage, and so on. That's the reason why. And the masking is usually negative infinity, because if you do softmax normalization, if you recall the formula for softmax, is going to be e to the power of something. So e to the power of negative infinity is going to be 0, right? And when we think about a 0 score, it means that, oh, basically the word I in the first query is not going to have access to M and not, and only have access to I itself. So that basically means that for those in the mask, the final result of that is that it won't have any similarity score, which is going to be 0. And it kind of makes sense, because we don't want to have similarity calculation for out of order words in a sentence. So the sentence, remember, there is an ordering, and it must not be shuffled around. Now let's discuss about the grouped query attention, which is another variant of multi-head attention. So this is more specific towards the implementation side. So when we think about the multi-head attention, if we recall the previous scheme, for each of the query heads, we will have its own key head, and then of course we're going to have the value heads, right? But the reason why this is not good is because of the memory bottleneck. So the operation itself is not slow, but when we apply to a hardware accelerator like GPU, the input-output or the data transfer in between memory regions is actually very slow compared to the calculation itself. So that's the bottleneck. So we want to kind of slow down the operation in a sense, or we want to localize the calculation so that they belong in the same memory region, so that the calculation and the I/O operation or the data transfer is actually balanced, and they kind of finish at the same time. So it's not bottleneck. So an extreme version of this would be, for example, if you have a lot of query heads, you will have only one key head that you're going to copy for each of the query heads, and you will have only one value head that you're going to copy for each of the query heads. But I think you can already see the problem. The problem is that you reduce the number of parameters, and if you reduce the number of parameters, you will get the performance degradation. So basically the performance is not really that good compared to the full lot of heads, different heads that you can train on. And so if you want a balance in between multi-head and multi-query attention, it's some grouped query attention. So you will have a group of query heads. You're going to serve them with one value head and one key head. And so you're going to copy less amount of time, but you get the benefit of both the performance, which is not that bad, and more importantly, you don't get this memory bottleneck. Okay, so the next operation is the feedforward. So this is compared to the previous operation that we have, this is non-linear. That's because we have this activation function of x multiplied by the sigmoid of x over here. So the sigmoid of x, you can think of it as compressing the value of x so that the output is between 0 and 1. Okay. So basically, when we have an input of batch sequence length, hidden dim, of course, you're going to kind of upscale this into an intermediate dimension, apply the activation function element-wise, and then you get this gate, which has the same dimension. Go back to x, you're going to upscale it. This time you don't apply the activation function, and then you get this up. What happens next is that you're going to multiply gate and up element-wise, and then you're going to multiply that by WD, which translates from the upscaled dimension into the original hidden dimension, so that we match the output to the input dimension. Now we are going to discuss the last linear layer. So after we have gone through all of the operations in the LLaMA architecture, we should get an output that's already highly contextualized and interconnected in a semantic way. So we have the batch sequence length hidden dimension. Now we are going to project this hidden dimension to the vocabulary size. So what we will finally get is that for each of the words in the sentence, we get a probability distribution across the vocabulary, and the probability distribution, if the model is well trained, should have the largest probability for the next token. Like for example, I know that the example here is not representative, but if the model is trained correctly, then the word am in the vocabulary should have the largest probability, and that's because we have trained the model in a sense so that the next word following I is am. Remember the auto completion objective that we have previously. So the final decision making of the model is the algorithm called the sampling. Okay, so let's think about the table that we have here and just select the first row. In this context, I have the word I and I'm going to predict the next word, right, using the probability distribution that we already have. So the first method is called the greedy. So the next token is the one with the largest probability. So I believe that that's the natural decision that we will have already made. So the largest probability that we're going to take is going to be M, right? And that's it. It's very deterministic and there is no randomness. But if you want some randomness or some kind of a more optimal decision, the next decision is the top K, where we will select K tokens with the largest probability. So remember that we will sort this first row here and keep the index of the vocabulary so that we will select K tokens with the largest probability. So, and then we are going to sample from this distribution so that for all of the other words that are not the top K vocabulary, they will not be selected. But the sampling still introduces this kind of randomness. The next one is the top P, quite similar to top K, but we are not choosing the K tokens specifically. Like for example, first we sort the probability value and then we set the P. So we are going to compute a cumulative sum for each of the tokens with the largest probability. We are going to sum each of the probabilities from the largest to the smallest. And once we have reached the sum to be larger than P, we are going to cut off the remaining tokens, right? So, and then we will sample from this remaining distribution. So a bit of note, since we are removing tokens here and everywhere, when we try to cut off the unused tokens, basically what we are doing is we are going to mask it with negative infinity, and then we are going to apply another softmax, so that those tokens with negative infinity will have the softmax value of 0, and then for all of the remaining tokens that are selected, they will be a probability distribution which sum to 1. So in that way, we can get a probability distribution that is appropriately weighted, and there can be no way of selecting the tokens that are not in the selection space. So congratulations on making it this far. We have completed the text part of the language decoder. Now we are going to get into how we can process the images, right? So firstly, this image, we need to convert it into some kind of representation that has the same language as the text input, as I have said it in our introduction. So firstly, we will have a feature extractor, which is in this case is the vision transformer, and the architecture looks really similar to the LLaMA architecture. We have the norm operation, we have the multi-head operation, and there are some additional differences when we compare image inputs into texts. So firstly, we will have this image patching. We will discuss about this special CLS token, and we will discuss about the multi-head attention. So firstly, the image patching is quite intuitive. Firstly, if you have a whole image, you're going to divide them into smaller patches, and as we have seen from the diagram here, one token or one image patch is going to be one token, right? So this becomes one token, one patch becomes one token, and so on. So the way that we apply this kind of patching and embedding so that we can convert the image, which is two-dimensional in nature, into one single dimension, is we will do non-overlapping convolution operation so that we can get this image size. So suppose that our original input is batch we have 3 channels since the image is RGB, and then we have image size, image size. So we are going to assume that the image is a square at this point. So we're going to also assume that the patch size is going to be square. So basically, we are going to divide the image into smaller squares, and we have conversion from these 3-dimensional channels into these hidden dimensional channels. So if you remember that hidden dim, this is actually the embedding space. Now this embedding space is unique to the visual transformer. You can make the embedding dimension to be the same as the language decoder, but essentially hidden dim here, it actually means that how many dimensions of a vector you will allocate for one particular image patch. And yeah, so if you define image size and divide it by image patch size, you will get this particular variable n, which will be important later on. Okay. And the convolution operation is quite well known. Essentially, you will apply this kernel into the input, and basically suppose that you select this here. So basically, like it's some kind of sliding window, and then you're going to do for each of the position, you're going to do pixel-wise multiplication, and then you're going to sum all of the elements of the product. So, for example, you have the output of 8 here corresponding to 0 multiplied by 0 and so on. So the only non-zero elements are 1 multiplied by 2 plus 2 multiplied by 3, which is 2 plus 6, which is 8 here. So if you remember, our general input structure for the transformers is going to be batch, sequence length, hidden dimension. So, but previously, our final dimension is really the batch, hidden dimension, image size divided by patch size, image size divided by patch size, or batch, hidden dimension, n. So we will need to project them carefully so that it becomes this batch, sequence length, hidden dim. So this is the original input that we have. We are going to multiply the last 2 dimensions into batch, hidden dim, n squared. And then we're going to transform this into batch, n squared, hidden dim. So this operation sequence is very careful because you don't want to mix the dimensions around. I know that they kind of like sum to the same dimension. Like if you multiply them, they will have the same combination. But the way that you combine them is influential, so that you don't really combine one axis into another, and that kind of jumbles everything around, and it doesn't really make sense. And then we can see that n squared here is actually the number of patches in the image. So remember that the image is image size, image size. If you divide the one dimension of image size into n, you will essentially only get like one portion here, and then you will get one portion here. But if you divide it again by another n, you will have a grid, a 2D grid. Like basically that's what I have stated here, right? And so when you think about batch, sequence length, hidden dimension, and going to the batch, n squared, hidden dimension, you can see that n squared is actually the sequence length. Remember previously that I have said that each image patch is going to be 1 token. And if you have n squared image patches, you will have, well, the sequence length entirely. Now this is the layer norm operation, which is the one that we found here. The norm operation is not RMSNorm. So the RMSNorm is used in the language decoder, but the layer norm is for the image encoder. But they actually like, the computation scheme is really similar. Basically, you will have this batch, sequence length, hidden dim. You're going to take one particular row and apply normalization along that row. So basically this time, the EX is actually the mean or the average value or the expectation value, basically just the average of the row. The variance here is the squared value of the standard deviation, which basically counts how much variance in between each of these elements. So this is about spread of the range of the values in the embedding factor. And then you will have this epsilon, which is a small value. Be careful here. This also happens in the RMSNorm. So this small epsilon prevents calculation dividing by 0, right? So you must have non-zero denominator. And then again, you will have gamma and you will have beta. So gamma and beta are two trainable parameters. Now this is really related to how fission transformer is originally trained on. So there is something special about encoder, because encoder is trained so that it can perform this kind of representation or some kind of compression of the image. And to do that, you will have to pick one task so that the representation is really catered towards that particular task. For example, here we have image classification. So for example, we have an image of a building over here. That's the original example. And what we're trying to do is that, remember that one patch is one token. Yeah, we're going to add one token in the beginning, and that token is going to be passed on. And finally, the final decision for that is that it's going to be used as a classification. So basically, again, it's similar to the probability distribution. So you will calculate the probability distribution, this time across all of the different object categories. For example, you have a bird, you have ball, you have car, and so on. So if the model is trained correctly, it should have the highest probability for the building category, if there's actually a building category on the classes that we choose here. And that's actually the special CLS token, and I think you can already know why it's called CLS. That's actually because it's used for the classification of the object, of the image, sorry. And the number of tokens is now n squared plus 1. The plus 1 comes from this additional token that we just add. Now we'll get to the multi-head attention in the image encoder, and this looks really similar to language decoder with a few remarks. So firstly, grouped multi-query attention is not used, so each of the query heads will have its own key head and it will have its own value head. So there is no copying of the same key and value heads. That's the first thing. Secondly, there is no masking. So each of the image patch will have access to all of the other image patches. So remember, this is not causal language modeling. You're not predicting the next image patch based on the previous image patch. So if you want all of the different image patches to kind of have this rich interaction, comprehensive image understanding is what we desire, but causal language modeling is not what we want. Okay. And lastly, the position embedding. Recall that in the language decoder, we have a rotary positional embedding. Now we use a trainable table. So what I mean by a trainable table is that for each of the vocabulary, now the vocabulary is image patches. Remember that one image patch is one token and correspondingly one position in the vocabulary. For each of the image patch, you will have an embedding, but this time the embedding value is trainable. So you will have, for example, in the patch 0 here, you will have the first dimension of the embedding, second dimension, third dimension, and so on. So all of the W's that I have shown in this table here are trainable. Now we'll get to the modality projection. So this is the part where we have our vision language or image language, and then we have our text language, and we will want to combine these two languages into a single common language that the model can understand. So there are two items that I want to discuss here, the pixel shuffle and the projection. So note that this is a special module specifically designed for projecting image into text in a sense. So the input is going to be the input is going to be images, more specifically image patches, as we have discussed before. So suppose that we have like for example, we have 4x4, we have 16 image patches here, and for one image patch, it will have its own hidden dimension, basically the embedding representation for that image patch or for that token. So what we want now is to reduce the number of patches, but we want a deeper representation. So we're going to do this for each patch. We're going to combine it in a row major order. Basically, it's ordered in this way. You have the pink, you have the orange, and then green, and then the brown, as we have shown here. Right? So a bit nerdy, but this is the dimension. The input is going to be from batch, n squared. This is the token. This is the sequence length or the number of image patches into embedding dimension. This is the same as this. So the n by n is actually h by w, and then we are going to separate this h times w into this H, W grid. And then again, you're going to divide H and W by its corresponding scale. So for example, we have 4 by 4 here. We are going to divide by a scale of 2, so it will become 2 by 2. Okay. And then next, we will have not only you actually divide the height and width by 2, so you get fewer tokens, you're going to scale the embedding dimensions by scale squared, right? So you'll get a deeper embedding dimension. But this is not the final operation. The final operation is that this embedding dimension multiplied by scale squared, you will need to project it into the LLM's hidden size, so that both the image tokens and the text tokens, they have the same length or the same dimension for their embedding factors. So you're going to project this using a linear layer. And yes, congratulations, you've made it this far. Now we can construct our vision language model. So we have our visual tokens, we have our text tokens, and they both have the same embedding dimension. So now you can arrange the visual or image tokens into rows. Like for example, we have, for example, a 2D grid like this. You're going to do a row major. So it's basically like the same operation as before. You're going to put this one and then this one below it, this one on its place, and then you have put the fourth one below that token. So it's going to be like something like this, right? And this is the image tokens. You're going to concatenate it with a lot more text tokens. So what follows is actually a giant table of batch size, sequence length, hidden dimension. The hidden dimension is the same, but this time the sequence length is going to be the sequence length of the image tokens plus the sequence length of the prompt or the text tokens, right? And you're going to pass this input representation into LLaMA, and finally you will have the next token prediction. Remember that our vision language model, for example, let's take an example of image captioning. You have an image, you will have a prompt of please caption this image. The output should be generated word by word based on the inputs. So the inputs is actually the image concatenated with the prompt. Alright, so we have already constructed our final vision language model. Now let's discuss some curious questions. So firstly, is it possible that the model outputs visual token IDs? Like what I mean is that when we try to, in the previous slide, we combined all of the image tokens with the prompt or the text tokens. Is it possible for the LLaMA model, the final text outputting model, to output the image tokens, right? And the answer is no, because the output of the large language model is actually restricted to the vocabulary. And by vocabulary, I mean the text vocabulary. So it will not have access to the image patch vocabulary that I have shown earlier. And therefore, it will not output any visual token IDs. Unless we add them to the vocabulary of the text, of course. And the next question is that if image tokens are always visible, could the model overfit on them and rely too heavily on vision, ignoring text context? And how do you balance modality attention? So what I mean by this is that basically you keep the model, you keep the image tokens or the visual tokens available for the model for attention. So remember that in the causal language modeling, you kind of hide the next tokens because you don't want the model to autocomplete, assuming that it already knows what the sequence is going to be. But in this case, the visual or the image tokens, it will always be available for LLaMA for its own attention calculation. So maybe there is an implication of this. So the implication would be, is it possible that the model actually puts more attention to the visual tokens rather than the text or the prompt tokens? Maybe when you think about image captioning, you want to put more attention on the image modality rather than the prompts, because the prompt is just generate image captions. But you want to put what's happening on the image itself, and you want to put more attention on that modality. And maybe for other tasks, you will rather have the instructions to be more detailed, and you want to put attention on that prompt, on the text prompt instead. So how can you balance the modality? And my suggestion, if you want to dive in more detail, is maybe you can try varying the image resolution. If you have a lower image resolution, then there should be less information that you can get out of the image. But if the performance of the model stays the same, that means, of course, the model doesn't pay any attention to the image, which is bad. And the third question that I want to discuss is it possible to reduce multimodal hallucination by reducing the masking of the image tokens partway? So basically, what I mean by this is that in the very first prompt, we have all of the images in the tokens, and then you're going to concatenate it with the prompt tokens. But after you output your first word or the first token, you're going to hide the image tokens. So the images are only made available on the very first time step. So after that, you're going to hide the image. It might reduce multimodal hallucination, right? And then the fourth one is it possible that you can make multimodal transformers self-supervised by predicting masked image patches using autoregressive text generation loss? So if you don't understand what that means, here's what I mean. So remember that in the vision transformer, you will have a list of tokens, which is actually just one image patch. In BERT, which is a very specific language encoder, you're going to mask or randomly hide some of these tokens, and the output is going to predict what's going to happen with the input that you have just passed. So it's quite similar to fill in the blanks, and during training, the model can be forced to learn the answer of the fill in the blanks. But that's for BERT, right? In Vision Transformer, I don't know if they do this, but maybe there is a new room for doing this kind of masked language modeling, in which, okay, you try to remove or try to randomly mask some of the image tokens in the beginning, and then the output, you're going to force the output to be predicting or doing some kind of filling the blanks based on the tokens that you have previously hide. Maybe you can predict what's missing from the image patch using a word or text outputs. So it's a bit technical, but I left it vague purposefully so that we can discuss about it openly. Of course, that's not everything. Remember that the code is really like 500 to 600 lines of code. So there are lots of optimization that can be made. Like we can think of inference optimization. We can think of techniques like KV cache, quantization, pruning, and something like that. So I leave you to research on your own on inference optimization techniques. Of course, we can also change the vision encoder and the language decoder, and more importantly, how we can combine the text and the vision tokens. Maybe we do some kind of cross attention rather than doing a simple modality projection, linear and pixel shuffle, something like we have in this repo. And lastly, remember that our LLM is only specific for image, specific for auto-completion. So maybe you would want to make it some kind of chatbot so that it's more like ChatGPT. So you kind of like, you have an image, you have an prompt, and then you have a system prompt, and then you're going to have this kind of observation, this kind of conversations, and you can make it like instruction following or instruction tuning. So that's how you can tune the model to follow instructions, and then you can serve the model on cloud or on edge. See if you can make a robust system that can scale to millions of users. All right, congratulations on making it this far. If you have made it, I feel proud of you, and I feel proud of myself, of course, but more of you. I hope this can spark some meaningful discussion on vision language models, and I hope you will answer some of the open questions that I have. You will also explore the repositories on your own, and maybe we can have some kind of discussion. Feel free to connect with me through the YouTube comments or through my LinkedIn. If you know me physically, maybe we can have a coffee chat together, or maybe if you're in Singapore. Okay. With that said, thank you very much. And of course, I will have the references listed in the description and on the pinned comments. And if you want to see them, you can see them right here. Okay, I'm just gonna sign out. Bye bye, and thank you for watching until the end.